Primality testers. Is 789,483 prime? How do you compute this efficiently? Firstly, what is a prime number? A number is considered prime if it has no divisors other than itself that are greater than 1. For example, 5 is considered prime, 4 is considered not prime, 3 is considered prime, but 2 is considered prime. So the first algorithm we look at is brute force. We simply go from all the numbers from 2 until we get to the number we're checking and identify if it has a divisor. The time complexity of this is obviously linear, but space complexity is O1. Can we do better? The first observation is if we have an even number, then 2 is a divisor. Consequently, we no longer have to try other numbers that are even because they will all have 2 as a divisor, so we've already checked for it. So using this optimization, we reduce the time complexity in half. However, the factor is still On, which we want to improve. The second observation is given the decomposition of a composite number, at least one of the products will be less than or equal to the square root of n. As a proof, assume for the sake of contradiction that two of the numbers, x and y, are both greater than or equal to the square root of n. Then, we have the square root of n times the square root of n is equal to n, which is less than x times y. Recall that a decomposition is a series of numbers multiplied that, in a multiplicative decomposition, add up to n. So how does this even help us? It actually helps us because we know that we no longer need to verify any number past the square root of n. So by doing this, our for loop is actually iterating up to the square root of n, so we reduce our time complexity to O of square root of n, which is pretty good, but introducing the Sieve of Eratosthenes, which will allow us to find it even quicker. This allows us to return all the prime numbers less than or equal to n. It works by creating a list of consecutive integers from 2 through n. Then we begin with p equals 2, the smallest prime number. We illuminate the multiples of p by counting in increments of p, starting from 2p until we hit to n, and mark those in the list. If we find the first number greater than p in the list that is not yet marked, then we let p equal that number and repeat from step 3. Otherwise, we stop. All the numbers not yet marked are denoted as prime below n. So as an example, we take our list of numbers, we mark all other multiples of 2, like 4, 6, 8. Then we do the same thing from 3. We know that 3 is prime, so we mark all of its multiples. Then we continue from 5 and perform the same thing. We go through all of the different numbers that weren't yet marked that are greater than it. And eventually, we'll find that all the remaining items are prime. So this is the pseudocode for the algorithm. It's pretty simple. Took it off Wikipedia. If you're interested, you can pause the video and read it more in depth. The only remark I wanted to do is that in the nested for loop with j equals I squared, is that this is an optimization. Consider that you're on number 7, which is prime, and then we do 7 times 2 is 14, which is the first number we'll cross out. Turns out that 14 is 7 times 2, but it's also 2 times 7. So 14 would have already been crossed out by 2 times 7. That's why that for loop starts at I squared. So what is the time complexity of this? The proof is outside the scope of the video, but it's actually O of n log n. The space, unfortunately, is On. So the first optimization is we can reduce the memory overhead by a factor of 8 in most programming languages by performing bit-level compression, where we don't use booleans, which are 1 byte each, but instead we use something like a bit set in C++. The second optimization is avoiding checking even numbers because they all have a factor of 2. And the last one is actually an optimization about the memory. We may use more RAM than is available. We have poor temporal cache locality using this approach. Introducing segmented sieves, which allows us for leveraging the fact that we only sieve until the root. That is, we don't need to keep all the primality array for all the prime numbers, and instead only up to a square root of them. If we let s be a constant for determining the size of the block, we then have a ceiling of n divided by s blocks, where each block contains the numbers in the segments from ks to ks plus s minus 1. So this technique roughly computes the root n primes using the approach prior. Then for each block, we perform a sieve leveraging the list of previously computed primes. If you really want to understand, you can pause this video and look through this implementation, right? Go through exactly how it works. So the time complexity of this actually remains the same, but the memory complexity is reduced to root of n, which is the primes we pre-computed, plus s, which is our window size. Lastly, we also have probabilistic algorithms. The Fermat primality test, so given an integer n, we can choose some integer a coprime to n, and calculate a to the power of n minus 1 mod n. This is roughly equal to Fermat's little theorem, and we see that if the result is different from 1, then n is composite, otherwise it might be prime. So for example, if you try this, it doesn't work for 561. The time complexity is k log n, with k repetitions, because this is a probabilistic algorithm. So yeah, thanks for watching. Subscribe for new videos every Friday at 12 p.m. Eastern.